Hello everyone, and welcome back to our video series on precision battery test solutions. In this video, we'll discuss the control loop ICs and how they function. The current sense and voltage feedback amplifiers measure and condition the charge-discharge current in the battery voltage, but it's the control loop amplifiers that actually utilize this feedback to appropriately adjust the driver's input and thus its output. Once again, drift is a very important spec to consider. A change in offset can result in a discrepancy between the intended target value, whether it's a target current or a target battery voltage, and the actual value that the system sees. Also, because the error amplifiers often see their inputs pulled apart, this differential voltage can cause the protective diodes of some amplifiers to turn on and pull significant currents, which can damage the devices and cause accuracy issues. Therefore, it is highly recommended that MUX-friendly amplifiers be used in this socket. Over the next few slides, I'll explain how the battery test unit of our design actually works. It makes use of 3 control amplifiers, one to control the CC mode, and 2 CV amplifiers to implement the regulation and threshold voltage safeguards. The current sense amplifier, which gains up the voltage across the shunt resistor, provides feedback that is proportional to the current in the system. Let's assume for a moment our control DAC output goes from 0 to 5 volts. We call the midpoint of this range Vref over 2, for us 2.5 volts. Now, our system is designed to support both charge and discharge. We use the Vref over 2 point as the reference on the current sense amplifier. When 100 milliamps of charge current is present through the 2 ohm shunt resistor shown here, this results in a voltage of 2.5 volts after the gain. When 100 milliamps of discharge current flows through the same shunt, this results in a voltage of minus 2.5 volts. Therefore, when we sum this with the reference voltage, it becomes clear that at 100 milliamps of charge current, the output of the INA will be 5 volts, and that at 100 milliamps of discharge, the INA output will be 0 volts. This output is then routed to the integrating CC error amplifier. Because of the virtual short theory, the amplifier wants the voltage at its feedback node to match the voltage at its non-inverting input. Therefore, the amplifier will adjust its output accordingly to achieve this. By adjusting the non-inverting input, which we call the CC set point, we can make the system achieve a given target current. If we want 100 milliamps of charge, for example, we just set CC set to 5 volts, and the system will self-correct to achieve 100 milliamps through the shunt, and thus into the battery. To increase the maximum supported charge current, it's simply a matter of decreasing the gain of the current sense INA, as long as the limitations of the driver are respected. However, on its own, this control amplifier will only allow us to charge or discharge at a given fixed value. It will not respect the regulation and threshold limits on the battery without additional help. We could use the feedback from the battery voltage sense amplifier to modify CC set, but this would require adjusting the DAC output. Instead, we make use of 2 additional error amplifiers, which we call CV high and CV low. These amplifiers use the output of the battery voltage sense amplifier as feedback at their inverting inputs. Their non-inverting inputs are controlled by the DAC and are set to the threshold voltage, for CV low, and regulation voltage, for CV high. We'll examine these amplifiers one at a time. Assume for simplicity that the driver of the system is a power amplifier in a buffer configuration. When the battery voltage is less than the regulation voltage, the CV high amplifier output goes high due to the feedback capacitor, which acts as an integrator. This prevents the diode D1 from turning on, because the output of the CV high amplifier is railed. But when the battery voltage is greater than the regulation voltage, the amplifier output will be pulled low. This causes D1 to turn on, pulling down the input of the driver. Because the driver input is a node shared by the outputs of all 3 error amplifiers, this means the CV high amplifier is able to counteract the CC amplifier by sinking current and pulling down the driver input to the regulation voltage. With the driver output and the battery at the same voltage, the current through the shunt goes to 0 amps. While this causes the output of the CC error amplifier to attempt to adjust to achieve the desired CC set voltage, the CV amplifiers are able to essentially overpower it. The other amplifier works in a similar but opposite fashion. When the battery voltage is greater than the threshold voltage, the CV low amplifier output goes low. This prevents the diode D2 from turning on. But when the battery voltage is lower than the threshold voltage, the amplifier output will be pulled high. This causes D2 to turn on, pulling up the input of the driver. This means the CV low amplifier is able to counteract the CC amplifier by sourcing current and pulling up the driver input to the threshold voltage. With the driver output and the battery at the same voltage, the current through the shunt goes to 0 amps, and the battery does not discharge any further. The diodes essentially act as switches to allow the system to charge at the desired constant current in CC mode when the battery voltage is between the regulation and threshold voltage without interference. Once either of those limits is reached, the appropriate diode will turn on like a switch to allow the appropriate CV amplifier to take control and prevent overcharge or over-discharge. By using this on-board solution, rather than requiring adjustment of the DAC output and associated delays on the microcontroller side, we are able to achieve true hands-off charge and discharge capability. Once the regulation or threshold voltages are achieved, the battery will be held at that voltage until the operator is ready to disconnect it. In our hardware testing, we made use of an OPA 189 in these sockets. However, depending on your system needs, you may want to utilize a different device. Visit the Precision Amplifiers section on TI.com to view and compare different MUX-friendly devices. Note that if you do not use a MUX-friendly amplifier, it is vital that sufficiently large current-limiting resistors are used to limit the input currents, as the differential voltage across the inputs will turn on the clamping diodes. Thank you for your time. Please visit TI.com for more information on battery test systems and other useful resources.